Okay, good to go? All right. Thank you, everyone, for tuning in to learn about the James Webb Space Telescope mission. Now, traveling back in time is the stuff of science fiction, but looking back in time is something that we can actually do, and it's made possible by the finite speed of light. If you look at the person seated next to you right now, you're not seeing them as they are. You're seeing them as they were a few nanoseconds ago. That's because it takes light a few nanoseconds to travel from that person to your eye. So when you look at the person next to you, you're seeing them as they were a few nanoseconds ago. Now, a nanosecond is a really, really small amount of time. So that transmission delay is imperceptible to us. But if we look at objects that are farther away, it becomes more pronounced. For example, if we had a magic switch that could turn off the sun, and we flip that switch, it would be 500 seconds before we saw anything happen. Why? Because it takes light 500 seconds to travel from the sun to the earth. So when we look at the sun, we're not seeing it as it is, we're seeing it as it was 500 seconds ago. If we look at the nearest star, we see it as it was 4 years ago. The center of our galaxy, we see it as it was 25,000 years ago, and so forth. And so modern astronomy involves looking back in time to understand how the universe formed and evolved. Now, the Webb mission was conceived in the early 1990s to connect the dots, if you will, between this famous image and this famous image. So what are these images? This is an image of the oldest light in the universe. It was obtained with NASA's COBE satellite. A Nobel Prize was awarded for that image. And it is what the universe looked like at the moment the universe became transparent, when the universe was only a few 100,000 years old. The pink and blue blobs that you see in that image are temperature inhomogeneities, which are the seeds from which galaxies will form and evolve. Now, at about the same time that the COBE mission recorded that image, the Hubble Space Telescope was launched. And the Hubble Space Telescope looked as far back in time as it could at the time to produce this image, which is the deepest image, the highest look-back time image that the Hubble had yet produced. And that image shows us what the universe looked like when it was about 1 billion years old. And so between this epoch that Hubble saw and this epoch that COBE saw, there's a poorly studied epoch in this cartoon version of the evolution of the universe known as the cosmic dark zone. The cosmic dark zone is poorly studied because we haven't had the right type of telescope in space to study it. But it's of great scientific interest because this is the epoch at which the first stars and galaxies formed. And so we really, really want to study that epoch, and that was the original impetus for the Webb mission. Now, you've all heard the statement that space is expanding. What do we mean by that? Space is expanding. This analogy tries to explain that. Here you have, in this cartoon, a loaf of raisin bread dough that's been set out to rise. Now imagine that you're seated on one of the raisins. What would you see as the dough was rising? You would see all the other raisins moving away from you, even though you're not at the center of the expansion. No matter what raisin you chose to sit on, you would see exactly the same thing. This is a good analogy for what we mean by space is expanding. We don't mean that the galaxies are flying through space as if it was the result of an explosion, but rather the space between the galaxies, the space itself, is expanding. Well, what does this have to do with the Webb telescope mission? Well, we want to see the first stars and galaxies to form in that cosmic dark zone. And those objects emit their light in the ultraviolet part of the spectrum. But as that light travels to us through that expanding space, through that expanding raisin bread dough, its wavelength is stretched from the ultraviolet into the infrared. So to see that light today, we have to build an infrared telescope. All right, so everything we know about the space around us comes to us transmitted, encoded in starlight. And the job of modern astronomers is to extract that physics information out of the starlight. Well, to get all the information, we want all the light. But all the light doesn't reach the surface of the Earth. And so this is a major reason, primary reason, why we put telescopes in space, to get above the atmosphere of the Earth. Light, the so-called electromagnetic spectrum, comes to us in an infinite spectrum of wavelengths, from very, very short to very, very long. Our eyes can only sense light in this very narrow slice of wavelengths. Why? Because our atmosphere happens to be transparent in that very narrow slice. So that's the range of wavelengths of light that reach the surface of the Earth. Our eyes have evolved to be sensitive to that. But there's a lot more light to be had. The ultraviolet portion of the spectrum lies shortward of the violet. We can't see that light, but your skin could be burned by it if you stay at the beach too long. The infrared part of the spectrum is longer than red. Our eyes can't see that light, but your skin can sense it. If you hold your hand near a warm stove burner or a warm radiator and you feel the heat, what's happening there is your skin is sensing the infrared light that's being emitted by the warm object. The Hubble Space Telescope was designed to operate in the ultraviolet part of the spectrum and the visible, so it can't see that cosmic dark zone. The Webb telescope was designed to operate from the red end of the visible out into the mid-infrared in order to see the early universe. All right, now, the spaces between the stars in our galaxy and others, the so-called interstellar space, it's not a cold, empty vacuum. It's filled with all kinds of stuff, gas and dust, and plasma, and so forth. Here you have a giant cloud of molecular gas, molecular hydrogen, and in that cloud of gas, some new stars have formed. They're producing a lot of ultraviolet light, which is ionizing the molecular hydrogen of this cloud and causing it to glow and put out that visible nebulosity, as we call it. And this is a famous object called the Eagle Nebula. And the Hubble Space Telescope imaged a little part of the Eagle Nebula to produce this famous image called the Pillars of Creation. These brown pillars that you see here are filaments of that giant molecular cloud of gas. And you can see the filaments are opaque. Why are they opaque? Because the gas is mixed with lots and lots of dust. So the dust is blocking the light. And we really want to see into that, into those regions, because this is where stars are forming in these clouds. And if we look at this same field in the infrared here with the JWST, one can see that the infrared light can see through the dust to reveal the star formation action inside the cloud. And so this is one of the Webb's most powerful capability. Its infrared capability can be used to peer through heavily obscured regions in space. Here's JWST imagery of another molecular cloud like this. Here you can see that much the same phenomena is occurring here. Some newly formed stars have occurred. That the ultraviolet light from those stars is breaking up the molecular hydrogen. You can see hydrogen streaming off into space. These are areas of active star formation. Here you can see all kinds of jets and outflows. In this image, the JWST is showing us star formation like we've never seen it before. Now, we know the basics of how stars form. We have these giant molecular clouds in space, and they collapse onto themselves due to self-gravity. And as the cloud collapses, the pressure inside the cloud goes up. And when the pressure inside the cloud goes up, the temperature goes up. It's much like when you fill your bicycle tire at the gas station. When the tire is fully compressed, it's a little bit warm. Well, the temperature in the cores of these molecular clouds get really, really, really warm to the point where nuclear fusion can occur, and then the star is formed. And when the star is formed, it's typically surrounded by a disk of material. You can think of this as material left over from the star formation. It's called a circumstellar disk. And those circumstellar disks are of great scientific interest because they are the birthplaces of planetary systems like our own. And so the Webb will do a great deal of work on studying planetary disks. Now, when planets form in these disks and begin to orbit the star, the planets sweep up that material to cause the disk to take on this sculpted appearance. And here you have radio telescope imagery obtained with a giant radio telescope in Chile of these sculpted disks. And so by observing this sculpting, we can infer the presence of exoplanets without even having to see the exoplanets themselves. And the Webb will do a great deal of this type of work. Here's an example. This is a circumstellar disk around the star Fomalhaut. And here is the Hubble Space Telescope imagery of Fomalhaut. And here you can see with the Webb telescope, we see so much more. We see all this inner structure. We see, possibly planets or density enhancements here in the disk. So the Webb is giving us a really new view of planet formation. Here we can see a circumstellar disk edge on, this little black line here with outflows shown as you can see here in the model. And so here is an area where planets are forming, right before our eyes. Here's another example seen edge on with these giant bipolar outflows from the young star. Here is the closest star-forming region to the Earth. It's about 400 light years away, and in this image there are about 50 new stars forming whose mass is similar to the Sun. The Webb shows us these processes in unprecedented detail. Now here you have an artist's rendition of the debris disk around our star, the Sun, alongside a map of where that debris actually exists. These are the so-called Kuiper Belt objects. These are chunks of ice and rock left over from the formation of our solar system that are still out there in the outer solar system waiting to be studied. And so we put special tracking capability, non-sidereal tracking capability, into the Webb telescope to allow us to study these Kuiper Belt objects. Now, some years ago, 2014, we obtained our very first image ever of a Kuiper Belt object. NASA's New Horizons mission, which was a Pluto flyby mission, when it finished the Pluto part of the mission, we sent it on to image this Kuiper Belt object for the very first time. And surprisingly, it turned out to be two objects fused together. And this has since been computer modeled to result from a low velocity collision, a few meters per second collision. It's been shown that these two objects can fuse without either one being destroyed. And this is of great interest for theories of planet formation, in which planets form by successive agglomeration of smaller particles into larger ones, eventually producing a planet over 10 to the 8 years or so. The Webb will do a lot of work on the Kuiper Belt. The Webb will also use its non-sidereal tracking capability to observe the planets of the outer solar system. And some of the most interesting work that the Webb will do in our solar system is on moons of planets, specifically Europa, a moon of Jupiter, and Enceladus, a moon of Saturn. It may be the case that most of the liquid water in our solar system is not on the Earth. These moons are believed to be ocean worlds, worlds that are covered with a vast ocean that is in turn covered with a thick crust of ice. Tidal forces act on that ice, causing it to crack, and it leads to a geyser-like phenomena with water ejecta escaping into space through these cracks in the ice. Now, this may be very important for the search for life in the universe. We know from studies of the mid-Atlantic ridge here on the Earth that life can thrive completely independent of the sun on chemical energy in these volcanic vents in the bottom of the Atlantic Ocean. And much the same thing could be happening here on Enceladus. This is a Cassini spacecraft image of this ejecta. And with JWST, we have spectroscopically measured this ejecta to determine what it is. It is water. And we've discovered that Enceladus is left this giant trail of water behind it as it orbits Saturn. So there's this giant water ring around Saturn resulting from this phenomena. So the Webb will do a lot more work on this to better understand this ejecta and this overall phenomena. This is the Webb's image of Jupiter and Uranus. The Webb, as an infrared telescope, is exquisitely sensitive to ice and rock. And these rings consist of ice and rock. So it's not a surprise that the Webb is showing us, rings of Uranus that we've, never seen before, like we've never seen it before. It's showing us the rings of Jupiter, lots of little moons of Jupiter that were too faint for flyby spacecraft to see. Here is Jupiter's great red spot. That's a storm that's been raging on the surface of Jupiter for about 400 years. Today we see that it's shrinking, and the Webb may help us understand why the red spot is red. We still don't know why the red spot is red. All right, when I was a graduate student, there were no planets known outside our solar system. Today we've discovered more than 5,000. With the implication that we believe that all stars have planets. And so that implies that there are tens of billions of habitable worlds in our galaxy alone. We don't know that they're inhabited, but we know that they're there. So the search for life is no longer the stuff of science fiction. It is a major science objective of NASA, and the Webb will play a key role in the search for life. Now, with Webb, we have learned how do we search for life on an exoplanet that's so tiny we can barely see it. We have learned how to take spectra of the exoplanet's atmosphere. We've learned how to measure the chemical composition of the exoplanet's atmosphere. We do it with a process called spectroscopy, whereby we spread light out into its component colors with special optics that allow us to see the emission and absorption of light by individual atoms and molecules in the exoplanet's atmosphere. Here's an example of the Earth, Mars, and Venus, and here are spectra of their atmosphere. So what is this? This is a plot of brightness on the y-axis and wavelength on the x-axis. And all these bumps and wiggles in that plot are due to emission and absorption of light by atoms and molecules, in this case in the atmosphere of the Earth. And we've learned how to determine which atom and molecules producing every bump and wiggle in the spectrum. So if the Earth had no spectrum, that plot would be a flat line. But when we see it not being a flat line, then we know that that planet has an atmosphere. And we will be searching for chemical constituents that are indicative of life. We do it with a process called transit spectroscopy. Now, you can imagine that when the Webb observes these alien solar systems, some of them will be seen edge on. And so in this cartoon, we have that configuration. We have a star, a planet, and then over here is our observatory and the data. Now, imagine that we observe in this configuration, and we take a spectrum. What do we have? We have a spectrum of the star plus the spectrum of the planet's atmosphere. Now we just wait a little while for the planet to move out of the way. We take a spectrum of just the star, subtract the two, and voila, we have a spectrum of the planet's atmosphere. I'm making it sound easy. Of course, it's profoundly difficult. The precision of photometry here is parts per million, but this has been turned into an exact science with the Hubble Space Telescope, and the Webb will do a lot of work on this. The Webb will primarily study planets that are somewhat larger than the Earth. The Webb can detect water vapor on an exoplanet that's a few times the size of the Earth. Now, if we're searching for extraterrestrial life, why do we care about water? It's not because alien life might get thirsty and need something to drink, but rather for the organic chemistry of life to occur on a planetary scale, one needs a liquid solvent to be available on a planetary scale. And water's, what we're most familiar with. Okay, so here's some examples of transit spectroscopy with the Webb on exoplanets. The first thing you can see here on this exoplanet, WASP 39b, is that the spectrum has lots of bumps and wiggles. So this planet has an atmosphere. And one can see that we've identified most of the constituents of this spectrum. We have sodium, we have water, we have carbon monoxide. In this particular exoplanet, we found sulfur dioxide. Sulfur dioxide is pretty interesting because it's produced by photochemistry occurring in the exoplanet atmosphere. This is a spectrum we just released recently, very exciting one, where we have discovered methane and carbon dioxide in this exoplanet, K2-18b, but we've also discovered dimethyl sulfide. Dimethyl sulfide is very interesting because on the Earth, there are no non-biological processes that produce dimethyl sulfide. It's produced by organic life type processes. And so it'll be interesting to see how this spectrum shapes up with further study. But this is some of the most exciting work that the Webb telescope will do on the search for life in exoplanets. Well, when we first put pencil to paper or marker to whiteboard on what kind of observatory we had to build to do that kind of science, we realized that we needed 7 times the light gathering capacity of the Hubble Space Telescope to see those faint primeval galaxies in the cosmic dark zone. And we needed Hubble's ability to see fine detail, angular resolution as they call it. And we needed an observing capability that extended into the mid-infrared spectrum. Well, when we realized those 3 things, we realized that we had 2 enormous problems that almost stopped the project dead in its tracks. Now, the Webb is flying, so we solved those problems, but let's talk about it. First of all, to get the 7 times the light gathering capacity of the Hubble, we needed a primary mirror that was bigger in diameter than the biggest rocket. That's problem number 1. Problem number 2 is that in order to build an infrared telescope, the telescope has to be made very, very cold. If we had infrared goggles on right now, we would see the walls, the floor, our bodies glowing in the infrared. Anything above absolute 0 emits light. So if we didn't make the Webb very cold, it would be blinded by its own infrared emission. How cold do we have to make it? Really, really, really cold, almost minus 400 Fahrenheit. And then and now, there was no mechanical refrigerator powerful enough to cool something as big as the Webb to such a low temperature. So those are the 2 problems that we had to solve right out of the box. So let's take a look at how we solved them. Let's talk about the thermal problem first. The Webb was not put in orbit about the Earth. the way most satellites are, in the way the Hubble Space Telescope is. Instead, we sent it to a special spot in space called the second Lagrange point of the Sun-Earth system. That's a mouthful. We just call it the L2 point for short. And it's about 1 million miles away from Earth in the anti-sun direction. Now, how does that help us cool the Webb telescope to minus 400 Fahrenheit? Well, as the Earth orbits the sun, of course, this pattern of Lagrange points, mathematical points, orbit with it. And so one can see that if an object is placed at that L2 point, the sources of heat on that object, the sun, the Earth, and the moon, will always lie in the same direction. So then we realized if we deploy a giant sun shield such that the telescope can always be in the shadow of the sun shield, we determined that it would cool to this very low temperature by simply radiating its energy away to the cold darkness of space. It required a very, very large sun shield, as we'll talk about, but this is how it works. So you can see that we sized the sun shield to be large enough that we could tilt the Webb 5 degrees toward the sun and 45 degrees away. We're still in the shadow. And now from this diagram, you can see that if we rotate the Webb about the Earth-Sun line, this horizontal axis, that's not going to spoil our shadow situation at all. And so now this arc that's 50 degrees wide turns into an annulus. And that annulus covers about 35% of the sky. So at any instant in time, the Webb can point at 35% of the sky and still be in the shadow of its sun shield. Now, as the Earth orbits the sun, now we're rotating about this vertical axis, and you can see that that annulus will sweep over the whole sky every 6 months. So every 6 months, the Webb can point at any spot on the sky and still be in the shadow of its sun shield and remain at its desired low temperature. Now, we didn't put the Webb exactly at the L2 point. We put it in a small orbit about the L2 point. Why did we do that? Well, on the Webb, we're generating electricity with solar arrays. It takes about 2 kilowatts of power to run the Webb. And so because we're using solar arrays, it's important that we keep the Webb out of the Earth's shadow. And so that's why we put it in a small orbit about the L2 point, to stay out of the Earth's shadow. All right, let's keep going. All right, the sun shield was the riskiest part of the whole mission. Those of you who are wondering, like what were they worried about when they were launching the Webb and all that stuff unfolded? We're worried about the sun shield, which was the highest risk part. The JWST sun shield has an SPF of 1 million. If you had this on the beach, you would be very well protected. It needs that SPF of 1 million to allow the Webb to cool to the very low temperature. It really is the size of a tennis court. It's about 70 by 40 feet. It has 5 layers. And each layer is made of a heat-resistant plastic-like material called caption. Each layer is thinner than a human hair. The sun-facing layer is coated with silicon, so it really looks pink in reality. The remaining layers are covered with aluminum. The sun shield has a special curved shape that helps it have that SPF of 1 million. Those of you who sew realize that to make something curved out of flat cloth, you need a lot of seams. And each layer of this sun shield is actually a quilt of 50 pieces, involving 7,000 inches of seaming. Here it's not done with needle and thread, but rather with thermal spot welds. So figuring out how to build and deploy the sun shield was one of the major challenges of the Webb telescope program. This is an example of some testing we did on the ground. Here, the sun shield is folded up inside this big pallet assembly. These plastic tables are there for gravity offloading. They aren't there in space. And this is, here we're showing how these telescoping booms pull the sunshade out of that containment pallet. You can see a person appearing in the middle there. That gives you a sense of scale. And then after it's deployed, these spreader bar assemblies around the periphery separate the 5 layers. This is exactly how it happens in space. If you look closely there, you can see the quilting. After these layers are separated, a cord that runs around the periphery of each layer is tensioned, and that's how the sunshade is deployed. All right, so deploying that, it involved 140 release mechanisms, 70 hinge assemblies, 8 motors, 400 meters of cable, going over as many pulleys. I mean, this is a mechanical nightmare, but it worked perfectly for us. Every one of those release mechanisms was a single point of failure, but we controlled that risk with lots and lots of testing, and we got permission to fly this design, and it worked perfectly for us. All right, what did we do about the mirror being bigger in diameter than the rocket? All right. We adopted something called a segmented mirror architecture. So instead of building one big mirror, we built 18 hexagonal segments that are mechanized to play together as if they were one big mirror. And that allowed us to fold the mirror and the telescope structure up inside the fairing of the rocket that we used. We used a French rocket called the Ariane 5. It's a 5-meter diameter fairing, and that was large enough to enclose this whole assembly. This rocket is launched from French Guiana, which is on the east coast of South America. And the payload was 6.5 metric tons. And the launch went very, very well for us. Now, those 18 hexagonal segments, the Webb mirror, they aren't made of glass the way most telescope mirrors are. We made them from beryllium. Why did we use beryllium? Well, as the telescope slews around the sky, points to different objects around the sky, there will be small temperature gradients that form in the mirror. And we didn't want those temperature gradients to spoil the shape of the mirror. So we had to find a material that had a low coefficient of expansion at this very low operating temperature of almost minus 400 Fahrenheit. It turns out that beryllium has that property. The beryllium starts out in a powder form. We compress it under tremendous heat and pressure to form a block of material called a billet. And then after we go through all the trouble to do that, we machine away almost all the beryllium. So this is a picture of the back side of a flight mirror segment. This is the front side with lab equipment reflected. And so we're lightweighting the mirror as much as possible. Whenever one designs something to fly, whether it's an aircraft or spacecraft, weight is a premium. And so these mirrors represent the current state of art of lightweight telescope mirrors, and they're about 6 times lighter than the Hubble mirror. All right, now we have another problem. How do we polish telescope mirrors? We rub on them with gritty stuff until they get smooth and shiny enough. That's a room temperature operation. So if we're going to polish the mirror at room temperature and then use it at minus 400 Fahrenheit, that means we have to put in the wrong shape at room temperature to get the right shape at the operating temperature. This is done through the magic of computer modeling, but computer modeling is not perfect. And so we had to follow an iterative procedure whereby we would polish the mirrors part way, put them in a specially instrumented space simulation chamber at Marshall Space Flight Center in Huntsville, Alabama. To cool the mirror segments down to their operating temperature, we would observe them with special optics test equipment to see how our model is tracking to reality. Then we would make adjustments to the model and complete the polishing. This is one of the reasons why it took so long to build the Webb telescope, but it was completely successful. So this is real data shown here. So this is a mirror segment at ambient temperature, and these colors denote relief, peaks and valleys, topographic relief. And we take that mirror and cool it to the operating temperature, all the relief is gone, and you have a perfect mirror figure. So it was worth the wait. It took a long time, but we got it done. All right, when we finally had all the optics polished and installed on the telescope, had the science instruments integrated to the telescope, and the spacecraft and everything, we then had to send it to the launch site. But when we had it fully integrated, the Webb is too big to fly. in a cargo aircraft. All right, so we sent it to the launch site in a special roll-on, roll-off transport ship, and we shipped out of Seal Beach, California, which is just south of Los Angeles. We went through the Panama Canal over to the launch site in French Guiana. The Webb was contained in this mobile truck-mounted clean room, which we were able to drive right on the boat and then drive off when we got to French Guiana. This is the first time that NASA's ever delivered a payload by boat, but it worked very well for us. All right. All right, now we're in French Guiana. I think we have no sound here for some reason, but all right. We're in an elevator, and we're riding up alongside the Ariane 5 rocket. There are work platforms set up along the way where people are working on the rocket and getting it ready to fly. We're going to the top, where the Webb telescope is being integrated to the rocket. And this is done in a very clean environment, as you can imagine. And here we're literally attaching the Webb telescope. It's folded in its launch configuration to the launch adapter of the rocket that you see here. So this was the very last view of the Webb telescope on Earth. There you can see they're integrating the fairing, or the nose cone, if you will. And then the rocket is rolled out of the assembly building on a crawler. It grows much slower than you see there. We rolled it out to the launch site, and then we launched it. It's too bad we don't have sound here, but. Okay, and we got a great launch. All right. All right. Once we got out there, the first thing that happened is we deployed the solar array and the high gain antenna. That's so we could become power positive. We're operating on batteries up to this point, and so we could begin communicating with the Webb telescope. All of those deployments went very well. This is how the telescope secondary mirror deploys. There are some thermal radiators and other equipment that deploys. And here you can see the wings of the primary mirror unfold much like a round drop leaf kitchen table. And so now we have those 18 mirror segments. And so each mirror segment is mechanized in 7 degrees of freedom, so we could adjust all the segments so that they can play together as if they were a single mirror. This is done interferometrically with special optics in one of the science instruments. And so when we first point this telescope at a star for the very first time, we have 18 separate telescopes. We get 18 images of that star. Then we have to move each segment to figure out which image goes with which segment, superpose them all, and then do a little bit of fine adjusting on each segment to make them exactly coplanar with their neighbors, and then we are left with a perfect single image. So this is something that we did during commissioning, and we don't have to do again. We just adjust the telescope once a month or so, very slightly. So the image quality from the telescope exceeds its specification by about a factor of 2. Now, with that image quality and the size of the mirror, the Webb is giving humanity its very first high-definition view of the infrared universe. We've never seen the infrared universe the way Webb shows it to us before. So this is what we had before. These are our prior infrared missions: the WISE mission, the Spitzer mission, and the JWST mission, all looking at the same spot in the sky. These 4 stars are these 4 stars are these 4 stars. And you can see the dramatic effect of Webb's ability to see fine detail, angular resolution. What's giving rise to that? It's just the size of the telescope mirror. The WISE mirror was 0.4 meters, the Spitzer was 0.85 meters, and the JWST is 6.5 meters. And that large mirror size compared to the wavelength gives one that clarity. Okay, we said we wanted to see the cosmic dark zone. We've done that. The Webb is able to look back in time to the cosmic dark zone and see objects at these very, very high redshifts or look back time. We're able to take spectroscopy of those high redshift galaxies to measure their chemical composition. It was thought that a true primeval galaxy would contain just hydrogen and helium. We haven't seen one of those yet. Okay. We are able to measure the shapes of galaxies at those very high redshifts. We were expecting the galaxies to be primarily irregular, but we see that many of them aren't and have very symmetric morphologies, much like we see in the local universe. We're able to measure the motion of gas in these galaxies. We can tell which gas is moving toward us, which is moving away from us, understand the rotation of the galaxy, and we can also measure we can map out the emitting region of various chemical components in the galaxy to put together a complete picture of these early galaxies. We can actually see the process of the universe becoming transparent. As these primeval galaxies begin to ionize out transparent bubbles in their surroundings, which eventually coalesce to produce a transparent universe. Here we can see this stage of development, actually pictures of these primeval galaxies ionizing their surroundings. This is a picture of the death throes of a star like the Sun. It's called a planetary nebula, has nothing to do with planets. And when a star like the Sun dies, it throws off its atmosphere to produce this big nebulous ejecta. When I was a graduate student, back in the 80s, I took the first infrared image of this object. Here it is right here. So that's what we saw in 1980, and this is the kind of detail we could see today. So it's a small improvement. This is the death throes of a more massive star than the Sun. Here, when a more massive star runs out of fuel and collapses, it produces a very powerful explosion, and the remnant of that explosion is called a supernova remnant. This supernova is called Cassiopeia A, and it occurred within recorded history. So only 340 years ago. And this is where all the heavy elements in the universe are produced. The calcium in our bones, the iron in our blood, the gold in our jewelry was produced in a supernova near the Earth. We've seen unusual phenomena with the Webb that we've never seen before. This is an example of episodic dust formation in this binary star system, producing this incredible bullseye pattern of dust emission. And the interpretation of this is shown in this cartoon. All right, so how does the universe work? How did we get here? Where are we going? And are we alone? These are the central questions of NASA astrophysics. And the Webb mission enables the next step in humanity's quest for answers to those questions, and you can join that quest. The people that do this kind of work, the people that build things like the Webb telescope and work with the data from the Webb telescope, come from all walks of life, in all backgrounds. There's a quote that I like to read. The book of nature lies continuously open before our eyes, but it cannot be understood without first learning to understand the language and characters in which it is written. It is written in mathematical language, and its characters are geometrical figures. That's as true today as it was 400 years ago when Galileo said it. So if you want to work in this, young people in the house or online, if you want to work in this sort of endeavor, have confidence that you can do that. Go to college, study whatever you love, But if that happens to include science, engineering, and math, this is a very realistic career objective, to grow up and build spaceships and do things like the Webb. If you want to get a sense of what it's like in college or in high school, NASA has excellent intern programs for every level, from high school to senior faculty, and this website provides one-stop shopping for how to apply for those. And then if you would like to get involved in this sort of research, but you don't want to go through all the trouble to get a PhD and become a scientist, NASA has a program for that too. We have something called Citizen Science. And if you go to that website, you can see how to join NASA research teams with whatever background you've got and really understand what this work is like. And despite the name of the program, you do not need to be a U.S. citizen to enter the NASA Citizen Science program. All right, what's next? We recently just launched the Euclid telescope earlier this summer. That's a European Space Agency mission on which NASA is a partner, and that telescope is designed to study dark matter and dark energy. Next year, we will commission the Vera Rubin Observatory. This is a giant ground-based telescope in Chile, and this will usher in a completely new type of astronomy called time domain astronomy, where the emphasis is understanding what changes in the night sky from night to night and over all different time scales. In 2027, NASA will launch the Roman Space Telescope. We're building it right now, and this is a telescope that's focused on also understanding dark energy, and it's developing technology to observe Earth-like exoplanets, and that technology will be applied to the Habitable Worlds Observer, which is the next big strategic, Webb-sized telescope that NASA will build in the next decade. Okay, so those are my remarks for today, and I'm happy to answer any questions if you have them.
Thank you. When you had said that the planets have or was it the moons have like a water vapor trail? Yeah. How would we gather like a sample of that to kind of like see what the composition was, and if there were any, different kinds of materials or minerals or things that we might not expect that could give us some answers?
Yeah, it's a pretty tenuous trail, but we'd have to sample it by going there. And of course, in solar system science, we have the option to go there. It takes a long time. The people that build missions like the New Horizons mission that I mentioned, you can liken that to European cathedrals, because the construction jobs spanned generations. So the people that built it wouldn't get to use it because it took so long to build the cathedral. Same thing with these outer solar system missions. The people that are getting ready to build the next mission to Uranus, they'll all be retired before it gets to Uranus. So, but we do have the option of going there, and that's how we'll ultimately understand.
I have a question. So, this I was talking about in my speech about an article that that the early moon and the late moon, the water differences might be different in the permanently shadow region as what we thought. And what I understood was that perhaps there's ice around the moon, like in the vapor, like a vapor trail kind of. Is there a possibility of that deposition of that? Either is that subliminal from the moon, or is that produced in the orbit of the moon and then deposited on the moon and maybe in different regions?
Yeah, I don't know about a tenuous, water atmosphere on the moon. You do see water in the regolith, the dirt of the moon. You do see water in the regolith on the sunny side. It's only a little bit, but it is there spectroscopically. And the hope is that in these permanently shadowed regions, there might be a lot of ice that could be exploited as a resource. But I'm just not knowledgeable about a gas phase that's accreting onto the moon.
Do you think that spectroscopy can be improved? And if so, how? And also, does it, if you had an even larger mirror, would you be able to see more then?
Oh, yeah. So we're always developing new instruments and new instrument technologies. And so, like I showed with that planetary nebula, the real difference there was the instrumentation. And so we're always improving our ability to do imagery and spectroscopy as detector technology improves and even optics technologies improve. And of course, a bigger mirror, we would be able to see more. Yeah.
I had a question, regarding the dark energy, dark matter mission. What is it that James Webb can and cannot see regarding dark energy, dark matter? Why would we need another?
We don't carry the right instrumentation really for studying dark energy as a phenomenon. It requires very large fields of view, very low distortion optics to produce very low distortion imagery. There's various methods by which they study dark energy, and one of them is baryon acoustic oscillations, where we want very wide field of view, low distortion imagery. Another method involves observing a certain type of supernova, and to get a lot of supernova, you also need a wide field of view. So each mission that we do is shrink-wrapped onto its science objectives with instrumentation that's designed very specifically for the science.
Would they need sun shields? Would they be occupying the same orbital space in the L2? Very similar?
They're going L2, but both Euclid and the Roman telescope are closed telescopes in a tube, so they don't need a sun shield.